Okay, so I put that on the board there just to clarify some things. If you, well, I should say when you were doing your homework for 1.1, either yesterday or the day before, you'll recognize that some of the concepts in the homework were not discussed in class. And that's because much of what that homework assignment was about would be prerequisite concepts for the class, things that you should know or be able to figure out before you actually got to this class. So I did have some questions over them, some of the problems, so make sure you're keeping up with that. I actually do have a quiz today for you, and that will be at the end of class, and it'll cover concepts from homework 1.1. That's just to make sure you kind of understand what my expectations are, all right? So we'll do that at the end. As far as the solutions for the homework, because Chapter 1, Section 1, and Chapter 1, Section 2 are prerequisite concepts, I don't have videos for those for the homework problems. But starting at 1.3, the homework solutions, you'll have videos for those from here on out, all right? Yeah, not every concept that I cover, or not every concept in the homework is covered in class. So as we move on, if you see something in the homework that just looks completely foreign to you, that's because I expect that you could read that problem and figure out what to do. In other words, from what you've been shown in class, you should have enough to be able to do that problem. Are you going to go over here? Yes? Okay. You're going to have a little cameo there on the video. I hope you don't mind. Okay, and as long as you're keeping up with your homework, I will keep the quizzes and exams, especially the quizzes, similar to the homework problems. The exam, similar, but also I'm taking problems that we do in class and just kind of, putting together my own thing, all right? But if you're doing your homework, you're going to be fine doing it and understanding it. Any questions over homework or anything I'm discussing here before we start? Okay, I have, I think I've decided to not use the clickers. You know those little things? I was doing it in my class the other day, and it's more trouble than it's worth, I think. And also it takes up real estate on my board, and I'm just not going to do it. Yeah, oh well. So instead I'll go back to the old school where you're just going to initial next to your name when I take attendance. So I'll pass this around, and let's go ahead and just get that going around. So go ahead and initial for Tuesday and today next to your name. If your name is not on this list, put your name on the bottom, and then make sure you talk to me about, let's make sure you're actually enrolled in the class and you didn't get dropped by accident or something. Okay, so let's continue with the material we were covering from Chapter 1, Section 1. This was the last thing that I wanted to discuss, and you should have seen something like this in your homework, problems similar to this. So what we want to be able to do later in this class, remember I talked about, one of the main things here is to try and find the highest points and lowest points on a graph. Well, a lot of the times when we do that, we actually have to take some physical problem and turn it into some mathematical statement or equation. And so these things here, just to get us kind of practice doing this. So let's see, let's look at the first one. We want to express the area of a circle as a function of its diameter. So when you think about the area of a circle, hopefully everyone in here knows the formula for the area of a circle. Yes? So we're going to do this one first. The area of a circle is what? Pi times the radius of the circle squared, right? So right now, if we look at this equation, you could say that the area is a function of the radius. In other words, since A is isolated, that means that if someone were to supply us with a value for R, we would be able to determine the value of A, right? So you could write this as A is like a function of R, and it's equal to pi R squared. Do you understand that? So A is a function of R. What we want is to express the area of a circle as a function of its diameter. So we want to come up with a formula where somebody's going to feed us, I'll use lowercase d, someone's going to feed us the diameter, and we should still be able to compute the area. So this one's a pretty straightforward problem because we actually know the relationship between the diameter and the radius of a circle, right? So the radius of a circle is the distance from the center of the circle to any point, and the diameter is just twice that, right? So we know that the diameter of a circle is just double the radius. So if we want to come up with this formula where our area depends on the diameter, then what we need to do, I'll go back to this one, is we need to somehow substitute or replace that r with something that has d in it instead, right? So if I'm going to replace this r, I come back down to this equation that I know, right? This is my relationship between r and d, and I solve it for r. Okay, so if I, let's say, take half on both sides, half the diameter is the radius, and now I can take this value, or this expression for r, in terms of d, and replace it in that formula, right? We good? So this will become pi, and then what squared? 1/2 d squared, right? And that is correct. I mean, like, we are kind of done at this point, but let's go ahead and just finish up the algebra here. We can square that, can't we? And when you square it, you would square the 1/2 and the d, so you get 1/4 pi d squared. And now your area is a function of the diameter. Is that one pretty straightforward? Any questions over that? Yes? Uh-huh. I'm sorry? How did I come? Oh, when you square this quantity, you have to square both, right? Did you say sorry?
Yeah.
No, don't apologize. It's okay. All right. First one, we okay? All right, look at the second one. Express the volume of a cube as a function of its surface area. So this is going to be a little bit different. Not as straightforward as the previous problem. So express the volume of a cube as a function of its surface area. So do we know anything about the volume of a cube? And a cube we have to, I guess, know coming in here, right? That a cube is just this box where all the sides have the same length, right? That's a cube. So do we know what the volume of this of an arbitrary cube would be?
S cubed.
S cubed. So S, you're saying, is the length of a side. So if we call this side here S, then that would be S, and that would be S. Oh, by the way, when you draw like three-dimensionally like that, you know, you draw like a square, and then you just kind of go back, 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 down, across. That might be hard, easy for different people. I mean, it takes time for some people to get that down. Okay, so you called it S, right? We could have called it X. We could have called it anything we want, L for length, whatever. But here we've assigned it S. So the volume of this would be what? S cubed. S times S times S. So that, again, is a formula that you kind of would have to know from your experience, in mathematics in the past, right? All right, so right now our volume is a function of what? It's a function of S, right? Our volume is a function of S, where S is the length of the side of the cube. But we don't want that. We want the volume to be a function of the area, right? The surface area of this cube. So that means we kind of need to know a relationship between S and the area of this. Surface area, that's like if you tried to paint the whole thing, right? Yes?
Is it 6S squared?
Is it? What do you think? Yes?
Yeah.
Okay, so let's see. If we want to find the area of just that first front face, the area, not the volume, right? The area would be S times S, which is S squared. So the area of that little piece is S squared. And then all 6 sides, right? We need all 6 sides together. So we'd add them up and we get 6S squared. So the area, I'm going to write this as a different equation over here. The area is 6S squared. And see, now we have a relationship between S and A, right? And so what we'll do here is what? solve for s, right? And then whatever we get for s here, we plug it back into this formula, and now we have a relationship between volume and area. So how would you solve that for s? Okay, divide both sides by 6. I'm gonna divide by 6, but I'm gonna write it this way. Is that all right? Dividing by 6 is the same as multiplying by 1/6. And you'll see as we move on in calculus that we kind of go away from this sort of notation when we're writing things. We always like to have our constants out front. So you see how I have the 1/6 in front? That's going to make your life easier later if you get used to this idea of just pushing it out front. All right? Okay, so I'm almost there. I've got s squared, but I need s, right? So what will we do to get s? Square root on both sides. Now, a little discussion here about taking the square root on both sides of an equation. What do you have to do when you take the square root of both sides of an equation? What must you always do, or must include? Plus and minus, right? So if you are ever sitting there doing any algebra problem for the rest of your life, and you take the square root on both sides, you must do plus or minus, all right? So I'm going to say plus or minus this. Now this side is going to be plus or minus the square root of 1/6 a equals s. Now we are going to throw out the negative one. Now why are we going to throw out the negative one? Because s is the length of the side of a cube, and we are going to assume that the length of anything is negative. I mean, it can't be negative, right? So algebraically, we have two possible answers, but within the scope of the problem we're working, only one of those makes sense. So we have s is equal to square root of 1/6 a. All right, now we go back over here and we replace our s with this, right? Okay, so let's do that. Continuing here, our volume is now going to be a function of a, and it's going to be this thing, right? What s is, the square root of 1/6 a, all raised to the third power. And that's fine. I mean, that's correct, but I'm going to go a little bit further. The volume as a function of a is 1/6 a to the 3/2. Okay, so what did I do there? Yeah, I used the fact that the square root of something, I'm going to call it u, is the same as u being raised to the half power, right? So if I take some square root of something and cube it, it's the same as taking that thing to the 1/2 power and cubing it. And then when you take something to a power, you multiply the two powers. 1/2 times 3 is 3/2. Okay, so this would be kind of like the calculus way of writing it, because you want to try and get, anytime you have roots in calculus, we try and get them to be rational exponents instead of radicals. It just, again, will make our lives easier later on. Questions? We have expressed the volume of that cube as a function of its surface area. Okay, last one. Express the surface area of a sphere as a function of its volume. So that means if somebody told you the volume of a sphere, you're supposed to have a formula that would spit out its surface area. That make sense? So let's draw a sphere first. So the way that I draw spheres is I start with a circle, like this. And then I put like a center point like this. And then I draw almost like a little ellipse in here, like that. And that gives it some sort of three-dimensional look, right? So that's a sphere. Three-dimensional solid. Or actually, it's just a surface, sorry. So do we know anything about the surface area of a sphere? That's probably something you don't know off the top of your head, right? Okay, so remember in class, or in last class, I said that in the back of your book, you have, or not the back of the book, on Canvas, you have these formula sheets, right, that I provide you, that you're allowed to print out. Do you see it there, sir? Yes? Do you see the area for sphere formula there? It's on the first reference page, right?
A equals
A equals 4 pi r squared. So that formula is coming from our formula sheets. It's saying, look, if you have a sphere that has a radius of r, then the surface area of this sphere, if you had to paint it, is 4 pi r squared. And if you take me for Cal 2, hopefully if you take anyone for Cal 2, they'll show you, they'll derive that formula. You can actually prove where that formula comes from. All right, we good? All right, so right now our area is a function of which variable? The radius, right? And that is not what we want. We want the area to be a function of the volume of the sphere. So now we need to somehow see if we can have a connection between the volume and the radius. That way I can replace this r with something, right? So then we go look at our formula sheet, and we see that the volume of a sphere is 4/3 pi r cubed, right? So if we're able to take this equation over here and solve it for r, right, then we're in business. So now we go through the process of solving that for r. And you know, I got y'all had those little sticks and everything and calling on people. So I left them in the box with the clickers. So I'll have those next class. Where's the sign-in sheet? I might just call people randomly off this thing today. Everyone sign in? Okay. All right, so I'm just going to kind of just pick names. There's nothing personal here, okay? Just going to kind of pick people here. We'll just go in alphabetical order. How about we do that? So how about Alfaro? Where's Alfaro? How you doing, sir? Okay, so if you were asked to solve this for r, like, what would you do? What would you do first? Okay, so what would that become if you move the fraction over? Are you in your mind, are you dividing by 4/3 or are you multiplying by 3/4? Multiplying by 3/4. So the other side's going to become a 3/4 v, and on the right side's gone. Okay. How about the pi? Divide both sides by pi, right? So you're going to multiply both sides by 3/4, divide by pi. So we're going to get something like this: 3/4 pi v equals r cubed. Everyone understand? Multiply both sides by 3/4, divide both sides by pi, and at the end, this is what you get.
Where did you get the 4/3 from?
Where did I get that from?
Yeah.
The formula on the reference sheet. Yeah, so this is something you may not know, and this one is probably something you don't know, so you have to go refer to something for that. Yes?
Could you times by 3 to get rid of the denominator, and then go over divided by 4?
And then divided by 4 to get rid of the numerator. And then divided by pi to get rid of pi. Okay, almost there. Cube root, right? Cube root both sides. So I'm going to take the cube root on this side. And you have to take the cube root of the whole thing. Can't just take the cube. What happens when I take the cube root here? Just get the r, right? Now, do I have to do plus or minus again? No. You only do plus or minus when you're taking an even root on both sides. So if it's square root, 4th root, 6th root, then you have to do plus or minus. If it's an odd root, okay, you don't have to. So that's it. That's r. It's the cube root of all that junk, right? The cube root of all that junk right there. And that gets to go here, right there, right? So now, our area as a function of the volume instead will be equal to 4 pi, this entire ugly thing, cube root of 3/4 pi v, all of that squared. Okay, so I just took my r, replaced it. There it is. And we can clean that up a little bit more, right? How about that cube root squared thing again? Can't we clean that? So we get something like 4 pi, what? All of this stuff raised to the 2/3. So this is happening because the cube root means raising it to the 1/3 power. And so if you take something to the 1/3 and square it, you get 2/3. All right. I think that's good. I mean, at that point we can stop, but I want to do a little bit more. And the reason I want to do a little bit more is because you see how you have a 4 pi here? And you see how you have 4 pi here? It's almost like these want to cancel. They don't quite cancel, but let's just, again, we're just making sure our algebra is somewhat solid here. Let me do something. I'm going to write the next line. I'm going to see if you agree and follow what I'm doing. So our area as a function of the volume will be equal to 4 pi times 3 to the 2/3 times v to the 2/3 over 4 pi to the 2/3. All right, so Luke, where's Luke? What did I do there, Luke?
You put the 2/3 exponent and yeah, sent it to the
Yeah, I basically applied this power to each of these things, right? And I'm allowed to do that because I have the only operations happening in here are multiplication and division. So you can apply those to everything. Now, the reason I did it is because if you kind of squint your eyes enough, you'll realize that this 4 pi, you could imagine that as being raised to the 1, right? And then you have something to a power over something to a different power, right? So what do you do when you have something to a power over the same thing to a different power? What do you do to the powers? You subtract, right? So what I'm going to do is I'm going to take 1 and subtract 2/3. And 1 minus 2/3 is 1/3. So my next line is going to look like this. 4 pi to the 1/3 times 3 to the 2/3 times v to the 2/3. I know that's weird, but again, we could have just stopped here, but I really want you to see, make sure everyone's okay with working with properties of exponents, things like that. And you could keep doing some things on this, but you're never going to really get rid of the 4 pi, the 3, and the v. They're all going to be there. You can change the way it looks, but we've taken care of the most, I guess, critical thing, which is we just didn't want to have that 4 pi in 2 different places, all right? All right, questions? Yes?
On the test, or you don't want us to simplify them?
No, I'm not going to necessarily, I'm going to really be looking for like this or this. I'd be happy with that. But as we go through the class, doing things like this should be something you're comfortable with. All right. Moving along. So this next section is going to go pretty fast, and there's not a whole lot to write. This is, section 2 is called Catalog of Essential Functions. So the way I look at this is like everybody's walking into this class and they have like this toolbox, right? Your math toolbox. And you got these drawers, and in one drawer is like all your algebra stuff, and then you got all your pre-cal stuff, right? And then stuff that you might have learned from some geometry class or something. So you got all these little drawers, right? So within the algebra drawer, there's this little section about functions and the functions that you should know, be familiar with, the way they look, the way they behave, all right? And we're just going to go through and make sure that these things are somewhere in your drawer, all right? So the first thing we're going to talk about are power functions. Power functions are functions that look like f of x equals x to a power, but this power that we're talking about here for power functions, this power, n, is I'll use this notation, n is an element of, how do I want to do this? I guess I'll do it. The natural numbers, you all know what the natural numbers are? Have y'all ever seen it? Everyone seems to have seen that before. All real numbers, right? This is a double struck capital R, right? That means like all the numbers on the real number line, right? When you see a double struck n, we're referring to the natural numbers. The natural numbers are 1, 2, 3, 4, 5, 6, 7. No decimals in there, like 0.5 is not there, right? So natural numbers is just like your counting numbers. So a power function is any function, at least the way we're referring to it here, is where our power is a counting number. 1, 2, 3, 4, 5, 6, 7, 8, 9. So our power functions all kind of have similar sort of characteristics. When the power is 2, it's a parabola, right? So it looks like that. When the power is 3, what happens is it changes. Instead of both sides going up, like the left side goes down, the right side goes up. But notice they all go through 0, 0, right? And then fourth power is going to look a lot like what? The squared. But they're not identical, right? Like the red one is the squared. The fourth power is the green. And then, let's look at the sixth power. Sixth power, look at the sixth power. It looks, again, like a parabola, but it's almost like it's being like pulled out like this, right? The higher the power goes, the further out it spreads out our parabola-looking thing, right? Okay, and yeah, if we could talk about the odds. Let's move on. Power functions. Now, negative power functions. So now we're talking about functions that look like this, but now you're not talking about the natural numbers anymore. You're talking about negative numbers like -1, -2, -3, -4. So I wonder if we have a notation for that. We do. So it is a double struct Z, which Z means integers. So I'll tell you real quick, just so we have it. The natural numbers is the set 1, 2, 3 forever. The integers is 0, 1, 2, 3 forever. But then the other direction, -1, -2, -3 forever that way. Does that make sense? So if I'm talking about a power function where my n is negative, this also includes the positives, doesn't it? Like Z includes the positives and 0. So what we do here is we just put a little negative sign on it like that. And that tells you, hey, that's all the integers that are negative. So that would be talking about -1, -2, -3, so on and so forth. You follow that? Okay. So what do you think this means? If you follow that notation, what do you think that means? All positive real numbers, right? If you put a negative there, that would mean all negative real numbers. All right, I'm going off a little bit here. All right, so if we have a negative power, right? These are rational functions. So this is what 1 over x looks like. Very important function. Comes into play quite a bit. We have an asymptote, vertical asymptote at 0, because at 0, all of these functions are undefined, right? 1 over x, 1 over x squared, 1 over x cubed. So all of these should have asymptotes at 0, right? Now, the other one I like here, other than 1 over x, is 1 over x squared. Sometimes I'll refer to this as the volcano function. It's like a volcano, but the center of the volcano, there is no real peak to it. It just goes forever, right? Okay. All right, so those are the power functions. All of these look familiar? Like you've seen these, right, in algebra? All right. All right, root functions. Square root function. The big important thing about the square root of x, that's the first one we're looking at, this one's root x, is that it has a domain restriction, right? You can't plug negatives into this. You can plug 0 in, right? You can't plug in negatives. So our graph should only exist from 0 and over. Now, what about if we do a cube root instead of a square root? Can you take the cube root of a negative number? Yes. Yeah, so when I draw this, I should not have a domain restriction. So that's what the cube root of x looks like. It exists both on this side and on this side. Now, what about the fourth root function? It should be a domain restriction again, because it can't take even roots of negative numbers. It's not exactly the same as the square root function, right? But it has the same basic characteristics, right? Like this. Almost like a parabola that's kind of been laid on its side and cut in half. All right, moving on. Polynomial functions. Oh yeah. So polynomial functions, spend a lot of time talking about these in college algebra. This is basically you taking power functions, like x to a positive number, like x squared or x cubed plus, and then you add to it another power function, then another power function. I think I have some examples here. So you'll see the functions appear here. So let's say I have a degree 4 polynomial with multiple x-intercepts. Let me give it. There we go. Okay, that's something like you would see in college algebra, polynomial function. Here it is, x to the 4th minus x cubed minus 30x squared plus 72x. That is a polynomial function. And in college algebra, we learn about how important that power is, right? The power tells us what? Well, the power and the number in front of it tell us what? Yeah, the end behavior, right? So if this power is like even and that's positive, then it does that. If it's even and negative, it does this. If it's odd and positive, it does that. If it's odd and negative, it does that, right? This test that we can run. So this highest power, right, the degree of the polynomial and the leading coefficient tells us about end behavior. And then we spend time in college algebra trying to figure out where these x-intercepts are, right? And sometimes it's easy, and sometimes it's hard. Sometimes you can factor this polynomial without much effort, and sometimes you have to use something like synthetic division, right? I know I'm asking you about things that were 2 classes ago, but in calculus we have to stir all this back up, okay? It all has to be here again. I'm not going to ask you to go graph a polynomial function, but you should know that kind of have a general idea of what this looks like. All right, polynomial functions. And then after that, you suffered through this in college algebra, rational functions. These were like the big daddy ones because you could have so many things happening here. No 2 rational functions really behave the same. And I should state that with a polynomial function, the ones we looked at before, all polynomials, you can draw them without picking up your pencil, right? Like every polynomial you can draw without picking up your pencil. Rational functions were the first ones that we see in algebra where you actually might have these asymptotes and slant asymptotes, things like that. And so graphing these by hand is a real pain, right? So what we want to just remember from this is that, you know, when you're looking at a rational function, it's a polynomial over a polynomial in that where do the vertical asymptotes occur? For any rational function, where are you going to find those vertical asymptotes where your function kind of like blows up? Anywhere what? Anything that makes the denominator 0, right? Now there are some cases where you can have a hole, but if you have a value of x that makes the denominator 0 and the numerator not 0, then you have a vertical asymptote. So we will be looking at those functions later. And then you took pre-cal, right? And so you learned about the sine function, right? The sine function has a period of 2 pi. It has an amplitude, right? So its range is from -1 to 1. And then you learned that the cosine function is almost identical to the sine function. It's just shifted over, really. It's like a little phase shift of sine, right? And then you have tangent. And tangent's where you first start running into some issues because you've got these places where your function's undefined. So you had vertical asymptotes. Do you all remember where the vertical asymptotes occur for tangent? Pi over 2 and negative pi over 2. And then so when I plot tangent x at pi over 2 and negative pi over 2, I should have vertical asymptotes. I'm going to have them again though, right? How far away is the next one going to be? What's the period? What's the distance to the next vertical asymptote? Pi. Okay, so we should have something like that. Let me get the other ones out of here, sine and cosine. What is the definition of tangent of x in terms of sine and cosine? Tangent is sine x over cosine x. That's the definition of tangent, right? So you're always going to have problems with this function when the denominator is 0, right? And the denominator is the cosine function. So if I put the cosine function back up here, everywhere the cosine function hits the x-axis, we should have a dotted line. Because everywhere the cosine function is 0, it makes that thing undefined, right? And then after that, we learned how to graph Oops, I should show something here. Okay, so the next one, cosecant, is the one I have here now. So what is the definition of cosecant? In terms of cosecant x is, I heard it, 1 over sine x, right? So that's going to have problems whenever sine is 0. And here's our sine function. So at every one of these x-intercepts, I'm going to have vertical asymptote. And then depending on how you learned how to do it, I mean, the way I teach in my class is to graph that, I have them graph sine first. And then everywhere it hits the x-axis, I have them draw a vertical asymptote. And then at the peaks, we just draw these like little u's like this. All right, so that's what your cosecant function should look like, right? And then secant and cotangent can be done similar ways, all right? So we should all be familiar with all 6 trig functions, their domains, their ranges, general idea of how they behave. Okay, now this is kind of back to college algebra, but we are looking at exponential functions. So exponential functions, all exponential functions look like this. A is called the base, right, of the exponential function. Are there any restrictions on what we can use for A? Like to be an exponential function, can I use any number I want here? Or is there some sort of restriction that I have for that? Like, can I use -1 as the base of an exponential function? No, I cannot. When you're taught about exponentials, you're told, hopefully, you're told that this number right here must be positive and can't be 1. So let's discuss that real briefly. Why can't it be 1? Why should we never let the base be 1? It's just going to be a straight line, because 1 raised to any power is still 1. So it's just going to be a solid line, and that's not really what an exponential function does. So we just say throw that case out, okay? And then why can't it be negative? Why can't it be negative? This is actually this is a thinking problem, okay? This is not so easy to answer, all right? But let's try it. Let's see. What if I tried to do this? What if I said, hey, everyone, let's do this. Let's try and graph this. So can we just like try some values? Like, what would f of 0 be? So plug 0 in there. Anything to the 0 is 1. So that would be 1, right? Okay. What if we plug in 1? We get -1, right? So far, no problem, right? What if we plug in 2? We get 1, right? What if we plug in 3? -1, right? 4, 1. Are y'all following me? Okay, so I mean, it seems like it's defined, right? Like it's actually, it is something, right? Let's see what that graph looks like. At 0, I'm at 1. At 1, I'm at -1. At 2, I'm at 1. At 3, I'm at -1. And then if I keep doing this, it's going to keep doing that, right? So I mean, that is a function. It's just weird looking, right? That's not why we throw out the negative. The reason is because I'm giving you some nice numbers here, right? Let me give you something not nice. So what would f of pi be? So in other words, what's -1 raised to the pi? Okay, now pi is on here, right? Like pi is here somewhere. Here's 4. Pi is like in here, right? There's pi, like a little bit past 3. What's -1 to the pi? So you try it on your calculator. See what your calculator tells you. Make sure you put the -1 in parentheses. What do you get? Domain error.
No real answer.
No real answer. Okay. So there is an answer to this, okay, but it's not real. It's a complex number, all right? And so we're not going to talk about it. All right? We're not going to talk about it.
Just out of curiosity, when would we talk about that kind of?
I'm glad you asked. So the question is, you know, you remember in algebra we talk about this thing, square root of -1, and we define it to be I, the imaginary unit, right? Yeah. Okay. And we do some problems, and we actually, depending on your algebra, we do actually kind of take a glimpse in here, and we talk about, you know, solving a polynomial or setting it to 0, and then you get some imaginary numbers for answers, right? You may have done that, you may not. It depends on your algebra. Did anyone graph these at all? Graph imaginary numbers? No? Okay. So in my college algebra class, I stay pretty far away from this because the way I look at it is this. It's almost like all we do in college algebra is just like open the door for just a second, well, window, let's say. We just open the window, we say, hey, take a look in real quick. Everyone looks and they see imaginary numbers, and then they shut it right on your face. And you don't see it again until after calculus 3. You have to take like linear algebra, difference equations, and then finally you take a class called complex variables. And that's where you actually start getting into this. And there's a reason for it, okay? The reason for it is this. And I'm gonna be off on a tangent here a little bit, but you asked the question, I wanna answer it. And I think it's kind of important to talk about. Like, why do you hear about this imaginary number? I'm gonna leave that. Why do you hear about this imaginary number and then you don't hear about it again, right? And in calculus, it's off the table. For us, it's off the table. A lot of times textbooks will say calculus, something about calculus of single real variable calculus. And they're very specific that we're talking about real variables. If you want to talk about imaginary numbers too, or complex numbers, then you take courses called complex analysis, where you do calculus with complex numbers. So here's why we don't do it, all right? Here's why we don't do it until way later. Because if I were to give you a function like this, okay? Everyone here is comfortable with the idea that that's this, right? Now that is a visual representation of what's happening, right? So that is a visual representation of this function. The way I want you to kind of rethink this is this. You have an input, right? And you have an output. So your input is going to be a number, right? So your input comes off of a number line. Let's say we plug in 3, right? And now your output goes through there, it gets squared, it comes out as a number, right? So it lands on the number line somewhere else. It lands at 9. Okay, so I could, say, hey, look, that number goes there, right? Everyone agrees that this is another way I could visualize that? Okay, well, let's be clever. Let's put this axis right here, this real number line, let's put that here and call that x. And let's take this one and turn it vertically and call that y. So you plug in 3, it spits out 9, and that point corresponds to both of those axes put together. Understand? So if you want to talk about complex numbers, imaginary numbers, what you have to realize is that when we use complex numbers, we don't use x anymore, we actually use z. And that's what lets everyone know you're using complex numbers. It turns out that if you hand me a complex number, that complex number actually is not on a number line. It's in two-dimensional space, not in one-dimensional space. So you have some complex number, some input. Boom, here it is, right? And then it gets sent through the function, gets dropped off somewhere in two-dimensional space again. After it gets squared, something happens to it. So if we want to try and visualize this function, I have to somehow combine this with this and put them together. And what's going to happen? How many dimensions do you have here? 2. How many dimensions do you have here? 2. And when you put those two together, you're going to need 4. And we live in three-dimensional space physically, right? So we can handle 3 dimensions. We all live in it, and I think we can visualize it, we can understand it. But what does something look like in 4-dimensional space? That's much more difficult to do, right? So you have to go through all the calculus to get you to the mathematical maturity to be able to handle functions that live, functions that can only be visualized with 4-dimensional space. And then you blow the doors completely off and you just kind of say, well, what if you have a function that takes something out of 5-dimensional space and drops it off into 4-dimensional space, then you need 9 dimensions to, I mean, it starts to get, so that's why we just like barely show it to you and then close the door, because we're not ready to handle this yet. Okay? I hope that answers your question.
Yes.
Okay, so this -1 to the pi is not a real answer. There's no real number answer to it, but there is a complex number. There's a complex number that this is a complex number. Let me just think for a second, I'll tell you what it is. It's, hold on. E to the I pi squared, should be. That's what it is. So if you have the I button on your calculator, some of you do, some of you don't. I believe, let me just rethink that, hold on. -1 pi e to the I theta, yeah. Pi, and then we're raising, yeah, that's right, okay. I haven't had to think about that in a while, okay? So that is what this is. But it's not real, it's not a real number. So we don't deal with it, so we don't have an answer to this. So when we put a negative base into an exponential function, we have problems, so we throw it off the table. All right, back to this. Can I say one more thing? Just one more thing? Okay. Imaginary numbers get a bad rap, okay? Because, well, it's like me telling you about my imaginary friend, right? Like automatically you're like, okay. So, and that's the way imaginary numbers were in the beginning. The first mathematician who started to talk about it, people were very skeptical, and they didn't believe it made much sense. And it got a bad kind of name from the beginning. But then it was shown later that the imaginary numbers are just as real as the real numbers are.
In quantum space.
No, just in general. As a structured set of numbers, the complex numbers with the imaginary unit in there makes as much sense as our real numbers do.
So, but like, did they come to that realization when they were searching or researching, or not?
They came to the realization when they were trying to prove. Okay, so we all know that with a parabola, we can solve this by, given a quadratic function, we can always find the x-intercepts using the quadratic formula. Yes? Right?
Yeah.
So if I give you that parabola, I give you the function that draws that, and I ask you to use the quadratic formula, what's going to happen in the quadratic formula? What are you going to get if your parabola is right here? Do you have x-intercepts? No. So what would happen in the quadratic formula if that happened? Like, you would get a negative under the root, and so you say, oh, I don't have any solutions, right? Okay, the way it was proven that imaginary numbers actually work is that they were trying to come up with a general formula for the solutions to a cubic equation. So, we can solve any ax squared plus bx plus c equals 0. We can solve that. There's a formula for it, quadratic formula, we're in business. But what if we have a cubic like this? Is there a general formula for this where we could just plug in and just do kind of like we do with this, right? And the answer is yes, there is. And it has square roots in it, just like the quadratic formula does. But here's the thing. We were using the formula and we were getting negatives under the roots. Okay, so what? So what? What can you tell me about every every cubic equation if you graph it? It has to go through the x-axis, right? Because if it's cubic, either the left side goes down, right side goes up, or the left side goes up and the right side goes down, right? In either case, you've got to go through the x-axis at some point. And so in that formula we had for this cubic, we had square roots of negatives, and we're like, holy crap, that still has to turn out to be a number. Like, that has to result in a numerical answer. And so we knew that they actually meant something. And then it started to take on what it really is. And my best analogy of what complex numbers are is this. It's so hard for me to not talk about complex numbers because most of my graduate work was in this, so it's hard not to. My best analogy is this. My daughter has a fish tank, but I'll use a fish bowl. So here, that's a fish bowl, I know. It's beautiful. So there's a fish. There's a fish. I'm going to give him a friend. Okay? So there's a fish in the fishbowl, right? Do you think these fish have any concept of my dog that lives in the backyard?
No.
No, right? Totally unaware. Their universe is that bowl, right? But there is a bigger universe outside of it. And what this is like the real numbers, okay? The real numbers are there, but the real numbers actually belong to a bigger universe of numbers. And that bigger universe of numbers is the complex numbers. And so every real number is a complex number. All right? Not every complex number is a real number, but every real number is a complex number. So it's kind of like you're in these classes, you're kind of stuck here, but then later on you're like, whoa. Okay? And so what winds up happening is that you can have really complicated problems that if you just live here, the problems are almost impossible to do. But if you live in that universe, the problems can become like almost trivial to do. And then so what you can do is you take the problem here, take off your real number goggles, put on your complex goggles, look at the problem again, go, oh, there's the answer, and then you send that answer back here. So it makes life a lot easier. All right, that's it. We're moving on. I'm done. If y'all want to talk any more about this, just come by my office. We can sit there and have lunch and talk about this all day long. Okay, exponential functions. If a is greater than 0 and not 1, they're either going to go like that, right? So we have an asymptote to the left. We have this thing going off to infinity to the right, unless we change the base. So here's 2 to the x. That first one was e to the x. The blue one is 2 to the x. Here's 1/2 to the x. What's going to happen? It goes that way. So if the base is bigger than 1, we have exponential growth. If the base is a fraction like 1/2 or between 0 and 1, we're going to have exponential decay. And then we have the logarithmic functions. And the logarithmic functions are just, what's the relationship between the log functions and exponential functions? What's the main relationship between the two? They're inverses, right? So that means if I graph e to the x, what's the inverse of e to the x? Natural log of x. There's its inverse. And if you graph the identity function, f of x equals x, these should be mirror reflection of each other. If I do 2 to the x and graph its inverse, what's the inverse of 2 to the x? Log base 2 of x. I get that, right? Okay, so what is it that we need to know about the log functions? What's the most important thing? I would say the most important thing about the logs is this. They have domain restrictions. They only exist to the right of 0, kind of like the square root. Except at the square root, you can plug in 0, right? Here with logs, you cannot plug in 0. And then there's something else that happens. What happens to log functions as you approach 0? Like if I start going this way, my graph does what? Takes off and keeps going forever, right? Like that? Okay. And then as I go this way, what does my log function do? It grows slowly, but it grows, right? And it just keeps going, all right? We're going to need that later to understand that behavior to answer some questions. All right, now this I'm blowing through fast. So this has to talk about, or this talks about like shifting graphs. So once you know all the like basic functions, then if you just add numbers either in them or on the outside or put negatives, it's either going to move it up, down, left, right, or flip it over or stretch it or compress it, right? So these are all our transformations. And then, I won't do that. These are just transformations, you know, where we can stretch things out. Nothing is stretching. Oh, here, I'm not showing the transformed one, that's why. So we can change the shapes of the basic sine function by just changing the numbers inside. Okay? All right, combining functions. So when you learn about functions, you're first taught the 4 arithmetic operations. And everyone's very comfortable with these because when you're in grade school and you're learning arithmetic, they teach you the 4 basic arithmetic functions, or arithmetic operations, right? Addition, subtraction, multiplication, division. So if they say, hey, take 2 functions and add them, everyone's like, yeah, I can add, right? Take 2 functions and subtract them, everyone's like, yeah, I can subtract. Multiply, fine. Divide, fine. So everything's great. And then they say, well, wait a minute, with functions you can do something that you can't do with numbers, and that's composition. Let's take a function and compose it with another function. So like when you're in grade school, they never ask you what's 5 of 4. Like compose 5 with 4. They say 5 times 4, 5 minus 4, 5 plus 4, but never this idea of composition. You can only do it with functions. So when we have this notation, f of g of x, it means that g is going to be plugged into f, right? If we switch that order, then the f goes into g. So I ask us here to take a look at this example and to add them, subtract them, multiply, and divide them. And I'm going to skip all of those except for the last one. I just want to make sure we all understand how we compose those two functions together. I'm going to assume you can add, subtract, multiply, and divide those. All right, let's go off our list. Who's up? Luke, I called you, right? Okay. Jasmine. Okay, how you doing, Jasmine? Okay. So, composition? Eh? Okay, so I'm going to write down f of g of x. That's the way we say it. And the definition of this is that you're going to take f and inside you're going to plug g, right? Okay. So when you start this, what would you do? So here's f and here's g. Okay, I'm giving that to you.
You would plug it in x minus x squared, where the x squared is.
Into that x squared right there. Perfect. That's it. Now I'm going to write it down a little more formally. I'm going to say f. What I'm going to do is instead of plugging x in here, right? Instead of plugging x into f, I'm actually going to plug in g, and g is this. So I'm going to do f of x minus x squared. So I'm taking that expression. It's going to go into f now. So if I replace that x with x minus x squared, then I replace that x with x minus x squared. So I'd get x minus x squared squared plus 1. So that's your composition. And then we could reverse it, right? We could do g of f of x. And we could expand that too, but I'm just leave it alone. All right. How about this one? I got myself a keyboard. Look at that. So I don't have to go over to my computer now. All right, so how about this one? Is it Sienna? Yes, Sienna. If I called y'all last time, I apologize. I'm just going in order here. Okay, so Sienna, I'm actually going to switch it up on you here. I'm going to ask for g of f of x. So that means that you're going to take f and go into g, right? So what are you going to do?
So, like, the x plus 1 over x.
That right there?
Yeah,
You're going to put that in here
Yeah.
and here, right? Okay, so let's do that. So I'm going to take g, and inside of g I'm putting f. F is x plus 1 over x. And then we're going to go x plus 1 over x minus 1 over 2 minus x plus 1 over x. So we have replaced that x and that x right there with those two expressions. And also notice I put the parentheses around this, right? Because I have to distribute that negative through. And of course we could try and clean that up and stuff, but that's the mechanics of composition. So be sure you're comfortable with this. We are actually not interested in doing composition. I mean, that's not something we need to be good at. I mean, I should take that back. We should know how to do this, okay? What we're interested in is going the other direction. So look at these. Look at this right here. Take a look at that function capital M of x. Sine to the 5th of x squared plus 1. Before we do this, are we all clear with the idea that this actually means that? that the fifth power here means that you are going to take sine of x squared plus 1